Good.
Okay, so the question we have now is how to, is what I told you before. So how to figure out the difference between a thermal state and some a thermal coherent state and some quantum and some incoherent superposition, which is what you get in a standard stat-mech ensemble. Think about it in canonical or canonical ensemble. Now, this brings us to, I told you at the beginning of these lectures that there are three ways essentially to characterize thermally isolated systems, the dynamics of thermally isolated system. One way is to think about non-equilibrium processes as thermodynamic transformation and define work statistics, entropy production, etc., etc. The other way is to think about them as in condensed matter physics. You think about a system, so compute expectation values of observables, correlation functions, response functions, etc., etc. And this is what have been done up to a few minutes ago, an hour ago. And now finally we get to some contact with quantum information. Now I'm going to touch just a few things in this context, because this really became recently a very popular field. For those of you who are interested, nowadays people are, as I told you at the beginning, are interested in circuit dynamics, quantum circuit models, quantum circuit myth measurements, etc., etc. They're interested also in seeing how complicated it is to simulate quantum systems with classical computers, or how necessary it is to use quantum computers in order to simulate their dynamics. And all of this is done with very interesting and very complicated quantities. One of them has a strange name of magic, the quantum magic, which is called a non-stabilizer, the stabilizer Renyi entropy in technical language. All of this is very nice, but I will not discuss it. What I will discuss is something that was that I understand in a reasonable way, let me put it this way, which is the physics of entanglement and to some extent the physics of OTOC, out-of-time order correlation functions. Now, both this, while, as I told you, entanglement entropies that were studied a lot in the context of non-equilibrium dynamics give you some kind of information about transient dynamics, how they grow in time, stationary state physics, what is the scaling with volume and with system sizes, etc., etc. I told you that you cannot hope to look at the entanglement entropy as a quantity that will give you information about the fact that you're dealing with a thermally isolated coherent system, simply because the subsystem entanglement entropy will always scale, if your system is ergodic and thermalizing, will always scale with the volume and will be identical to the thermodynamic entropy. So there is no hope to use it to answer Kitaev's question. So then we have to come up with something else. So one possibility is to use another quantity, which is called the quantum Fisher information. Now, since the physics of the quantum Fisher information is, and what it is related to is not very well known in the condensed condensed matter community, before telling you directly why this quantity is interesting in the context of ETH and non-equilibrium dynamics, let me give you a brief introduction to the quantum Fisher information, how it is important for certain type of quantum mechanical experiments, and how in principle it could be, if not measured, inferred from experimental studies. Now, the quantum Fisher information, first of all, this Fisher is not our Fisher. So if you come from condensed matter physics, there is a guy who invented, contributed a lot to renormalization group, field theories in condensed matter, etc., etc. That was Michael Fisher, and Matthew Fisher, his son, Daniel Fisher, his other son, etc., etc. This is another Fisher. This is Ronald Fisher. He's a mathematician. And Ronald Fisher did not invent the quantum Fisher information, but actually invented the Fisher information, which is a quantity that is very useful in classical statistics. I don't know if you have ever done experiments in your life, or if you've ever touched an experimental apparatus or tried to do something in that context. So I happen to have done, when I was a PhD student, my office was next to labs. So I spent some time in labs with my friends. And lately in my career, I also spent some time with statisticians because they were involved in fitting data for COVID. Don't ask me why. So anyway, and I learned something very interesting from them. Imagine that you have a set of data, right? You do some measurement, number of cases of COVID per day, and how many are sick, how many go to the hospital, etc., etc. And you want to give a sense to this data. So as a theoretical physicist, when you want to condensate some information into some physical object, what you say is, what is the Hamiltonian? Which was the question of my advisor every time I was entering the room and starting discussing some physics. What is the Hamiltonian? And you write the Hamiltonian and everything else follows. Now, for someone doing statistics, the concept of model is something else. What they have in mind when they say, I have a model for my data, is essentially have a distribution function. So a probability distribution that depends on a certain set of parameters. It has a certain functional form. And I am trying to infer the parameters, or to fit the parameters with which that this distribution has to fit in the best possible way the data I have and to describe reality. So one standard example, for example, that we all know and love from our undergraduate studies is the Gaussian distribution. So imagine that we have a certain set of data, and we want to infer from measurements fitting with a Gaussian distribution. We want to infer from measurement what is the value of theta, which is the center of the distribution itself. And with what is we want to know also with which precision we can at best infer this value. And it's clear that since you can distinguish two Gaussians only if the centers are farther away from their width, think about a bunch of data, right? A bunch of points. It's clear that the best precision with which you can determine theta is going to be set by what is the width of the Gaussian itself. Then it's obvious that the best, the fluctuations or with theta is going to be roughly equal to the standard deviation of your Gaussian, right? But, you know, in this case, it's pretty easy. We are dealing with Gaussians. What about some other distribution, some complicated probability distribution that nobody knows what kind of form has? So this is the problem that Ronald Fisher tried to solve. So what he had in mind was, imagine that I have a certain probability distribution P of x and theta. X at the random variables, theta is some parameter. This probability distribution depends on a certain parameter. And now I want to figure out what is the best resolution with which I can pretend to determine the value of theta given the parameters, given a certain number of measurements of data that are described by this distribution. Clear the question? No? So you make n measurements of a certain random variable, right? This random variable is described, you know that this random variable is described by a certain probability distribution that depends on a certain parameter theta. And from these values, you want to infer what is the value of theta, right? And the question is, what is the best accuracy you can hope of getting to determine theta? Okay? Now you can tell me how is this related to quantum systems out of equilibrium, etc., etc. We'll see that. But let's stick to this problem. So, in order to answer this question, Fisher introduced the concept of Fisher information. So, you know that information associated to a probability distribution to the outcome theta and to the probability distribution P of x is minus the log of P of x and theta. I don't know if you're familiar with this, but the entropy of a distribution, which is minus the sum over x, P of x theta log of P of x and theta, is just the average information. The average information is called the Shannon entropy in the context of information theory. Now,
sorry.
Yes?
The meaning of information.
What is the meaning of information? Oh, okay. I mean, why information is related to probability? Perhaps is the
What do you mean?
question.
Because in everyday life, I think information means not the same thing that you mean here.
No. You do mean the same thing. You simply don't realize. Let me explain you why. Imagine that you're driving in roads at night. I don't know about Ljubljana, but in Trieste, all lights are on yellow at night, right? So you always see yellow, 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 yellow. Probability of yellow is 1. Probability of other colors is 0, right? What is the information this yellow is giving you? 0. No information. I mean, the traffic light could not be there and it was the same. Imagine that you're driving during the day. You have a certain probability to see yellow, you have a certain probability to see red, a certain probability to see green, right? So let's say they are equal. So the information of the outcome is equal to the probability, right? Is minus the probability of the outcome to occur in a certain probability distribution. Same thing for letters. Imagine that my language was made only with the letter A, and I would start speaking and saying A, the time and nothing else. So what information would you get? Nothing. Information is related to the probability of occurrence of a certain string of words. And that's what you're decoding. So that is the idea behind this formula, right?
I'm always confused because typically when people speak, they can say 3 words which could mean the same as 1 word.
Okay, but that here you're entering very complicated, the difference between semantic meaning, you're complicating things. Let's stick it to the example of the traffic light.
Okay.
In that case, it's simple, right?
Yes.
So in that case, if you have only one color, there is no information at all. Probability is 1, and log of 1 is 0, and information is 0. That's it. No information at all. If you have more than one color, then you start getting information depending on the probability of the outcome. So this is the idea of the Shannon, of the concept of information in information theory. And the Shannon entropy is just given by the average of the log, so it's the average information and nothing else. So now imagine that now I want to figure out what is the precision with which I can infer theta. And the idea of Fisher was that this precision should be related to how the information changes if I vary the parameter theta, in a sense. Because, if I vary the parameter theta and there is no information change, then, it's practically undetermined, the parameter. If instead I have a large change of information, I will have a strong dependence. So what we tried to do was then to take a single derivative of information with respect to theta, and then take the average of it. And this, unfortunately, if you do the calculation, turns out to be equal to this, which is equal to 0 because the probability distribution is normalized to 1, right? So you take the derivative outside, integral of p of x is 1, and then this is equal to 0. So first derivative doesn't work, but luckily second derivative does the job. So the Fisher information is defined as integral dx I of theta and x squared. No, here there's a mistake. D theta squared okay. All right, and doing some now what is interesting of this definition, and then I'll switch to the quantum case, is that first of all, if you consider the case of a Gaussian, you do quickly the calculation and you will discover that this guy for the Gaussian is equal to 1 over sigma squared. But what is most important is that given this definition of information, one can prove a theorem which is called the Kramer-Rao bound.
Sorry.
Yes.
Is it possible to ask a stupid question? Why the average of derivative of information by theta equals 0? Because actually your derivative by one variable and integrated by another one.
No, because
so
you see, let me do it slowly. So this is equal to integral dx, the derivative of the log. So it's d theta p divided by p with a minus sign times p.
Yeah.
So the p goes with the p. Then this is equal to integral dx minus d theta e.
Okay.
But now the d theta, since here I'm integrating over x, the d theta I can take it out of the sign of integral.
Okay. Okay. That's
This
clear.
is minus d theta.
Okay, thanks.
Dx e, and this is equal to 0.
Good.
Okay?
Good.
All right. So the Cramer-Rao bound that I'm not going to prove, but you can find the proof in Wikipedia. Okay, you can find it in Wikipedia. That's the simplest place where you can find it. Tells you that if you have if you measure if you have m outcomes of your measurement according to this probability distribution, so x1, x2, etc., xm, then the best accuracy with which you can hope to determine your parameter theta is bound from below by 1 over n times the Fisher information f of theta. So you see that in the case of a Gaussian distribution, this is greater or equal than sigma squared divided by m. Now there is also another important piece of information that I can give you, is that this bound in classical system is saturated by what is known as a maximal outcome, well, I don't remember the precise word, is saturated by determining theta in such a way that the probability to get the sequence of outcomes x1, xm is maximal, right? So imagine you multiply the probability to get the first, the second, etc., and then you maximize this product over theta, and that's the best estimate of theta. Maximal. Yeah. The funny thing is that I repeated this word a few seconds ago in my head, and then I forgot it while I was talking. Anyway, so what has this to do with quantum systems? Imagine that now.
Sorry.
Yes.
Just the last question about this Cramer-Rao bound. So you have distribution of probability and it has a parameter, and how can we estimate this parameter based on distribution with this bound? But what is the ansatz from which this parameter exists?
So that's what I was trying to say. The bound is saturated by the maximal likelihood estimate, and that's what it is. By a maximal likelihood estimate, which consists in doing the following. You have a probability distribution that depends on theta, and you have a set of outcomes of your measurement, x1, x2, x3, xm. So you determine theta in such a way that the probability of having this string of subsequent measurements is maximal. So you maximize the likelihood of getting the result you got. Okay?
But theta, is it like in Gaussian function?
No. You're fitting your data with a model.
So
right?
For any model.
So what you do as a physicist is the experimentalist is doing a calculation, is doing an experiment, and you're fitting his data with what you call a model that is an Hamiltonian. So you take your Hamiltonian that depends on certain parameters, right? You calculate the correlation function, the whatever, you give it to your friend experimentalist, and he has to fit his data in order to find the parameters that are sitting in the Hamiltonian. These guys are doing something very similar conceptually, but instead of having an Hamiltonian, they have a probability distribution, okay? Which in this case is just a probability distribution of a single variable. It could be something much more complicated than this, but the principle is the same. So they're doing the same as what we do as physicists all the time. Okay, so Good. So now we come to the quantum problem. So can we translate this concept of Fisher information that is important for classical systems to something that is important for quantum systems, or that tells us how efficiently or how accurately we can infer parameters in a quantum mechanical experiment. So in order to do so, I have to define what I call experiment. So imagine that I have a certain density matrix rho, which I write in diagonal form as this, is diagonalized by a certain set of eigenstates. And now I imagine applying a transformation, a unitary transformation with a generator O to this density matrix. So that would mean doing, for example, e to the minus k theta O rho e to the I theta O. So this could be a translation. You know, translations are represented this way, rotations are represented this way. Anything that is generated by some unitary, from any unitary operator that is generated by some, you know, some observable, could be represented in this form. And now, doing so, I will generate a density matrix rho of theta. And now the question I have is, by doing measurements on this density matrix, what is the best accuracy with which I can infer the value of the parameter theta, right? So imagine that you have your favorite system, you apply a translation, but you don't know by how much you translated, right? In that case, P is always going to be the momentum, and X is going to be how much you translated your system, and now you want to infer by doing measurement on your system by how much what was the angle of rotation or the step of translation or whatever. So the question is clear, right? Or it could be, you know, magnetic field applied, whatever, right? So the answer to this is given by the quantum Cramer-Rao bound, which tells us that delta theta squared is going to be greater or equal than 1 over m f of q. Okay, first of all, I have to define what are the measurements, right? So here I'm assuming that when I write m, I'm dealing with a quantum system. So I perform the rotation, then I do a POVM measurement, and then, of course, I mean, that corrupts the state. I have to repeat the experiment, do another measurement, redo the measurement, etc., etc. So what I mean by M is the set of repetitions of this measurement with the associated outcomes that I'm doing. And f of q is the quantum Fisher information that has an expression that was found by Braunstein and Caves, that is f of q equal to sum over I and j minus pj squared divided by pi plus pj times I of j squared. So the p's here are these p's. So I'm assuming that I'm starting with a certain density matrix, and these i's and j's, I apologize, are just these eigenstates. Okay, so this is something that, I mean, we leave it as it is. If you're interested in proofs, I think you can find them in either in the original papers that are by Simone Montangero et al., or in reviews by Smerzi, Pezzi. It's a review of modern physics.
Is there an example of how is it used?
Yeah, I'm going to give it to you
Right.
in a second.
So let's say that we start in a completely mixed state, that
Yes.
all of these p's are the same, then this Fisher information equals 0, and so the lower bound is infinite.
That's interesting. I never thought about this.
It means that theta can be arbitrary and all of them will be fine fit. So that's why we feel we don't know the function that we're fitting, right? So if it's a constant function, it could be the same parameter. Then you do normalization, and all parameters will be good function with normalization. That's why we will be fine.
I think you're right.
So then any theta is
Yeah, for this case, because it's a constant function.
So, but wait a second, it is clear why it is so, right? Because if these are all equal, then rho is proportional to the identity. Then this rotation is trivial. And then this does not depend on theta. And then any theta would work. You see?
Okay.
And therefore the accuracy is infinite. So the delta theta, so if any theta would work, then delta theta is infinite.
Okay.
So
yeah, thank you.
that's why, so it's correct. I never thought about this, but it's correct. It's a, you know, this is a benchmark of why this expression is correct. Okay, good, excellent. All right, so another example you can work out is what happens what happens when the temperature is 0. So when you're dealing with not with a density matrix, but with some state. So imagine that P0 is equal to 1 and Pi is equal to 0 for I not equal to 0, right? So you have just one state that is sitting there. Then in this case, f of q is equal to 2 sum over j not equal to 0 of j or plus sum over I not equal to 0 of I. And this comes out to be, no, wait a second. Okay, let me write the final result and then we'll discuss it. 4 times, yeah, sure. Is 4 times O squared O minus 0 squared. Okay? I mean, these two terms, you get them from setting either pi equal to 1, so I equal to 0, and all the j is not equal to this one, or j equal to 0, and all the I is not equal to this one. And then this one, you get it because if you look at this, you can write it as sum over j from 0 to whatever, so you can include the 0, but then you have to subtract it, which is this term. Okay? So in other words, you obtain that the Fisher information for a pure state is 4 times the average of the fluctuations of the operator. Okay? And now, you see, think about it. When I write the Kramer-Rao bound, the quantum Kramer-Rao bound, what I wrote is this, greater or equal. Did I write it? Yeah, I wrote it, right? Greater or equal than 1 over m times f of q, f quant. Now, let's say that we are dealing with a pure state, like that one. So I would get the delta theta squared times the average of delta O squared is equal to, is greater or equal than 1 over 4n. Imagine that you're doing one measurement, so n is equal to 1. What is this? It's the Heisenberg uncertainty principle, roughly speaking. No? It's essentially the same thing. So if you replace this by an operator, this is going to be the angle with, by momentum, by an angular momentum, this is going to be an angle. If you replace this by a momentum, this is going to be a position, etc., 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 right? Conjugated variables. So it's essentially the uncertainty principle for a pure state. And what I'm stating there is a generalization of the uncertainty principle. Now, what is the problem of this Kramer-Rao bound? So the problem is the following, that in the case of a classical system, I told you that the maximal likelihood estimate is saturating the bound. So in principle, we know how to get the best accuracy for delta theta. In the quantum case, we know that there is a POVM that saturates the bound, but that we don't know which one it is. The proof is not constructed. And therefore, in principle, you cannot tell an experimentalist to do this measurement on your quantum system and you will be able to get the best accuracy in determining your version. You just know that in principle there is such a relation. Okay, so now what is the story now with this and non-equilibrium dynamics? Well, first of all, we have to figure out something important, that the Fisher information itself gives us important information about entanglement in our system. And this you can understand in a very simple way. Imagine that we are dealing with pure states. So again, we're dealing with our 0, And our Fisher information is, as we said, 4 times the fluctuation of favorite operator. And it generates the rotation on the state. And now imagine that we are dealing with a system that is super trivial. Super trivial means imagine a spin chain in which the spins are not correlated with each other, right? So each spin lives its own life independently. So my state psi is going to be a product over I of 1 to n of phi I. And I decide that my observable O is a local observable, for example, sum over I sigma alpha I. Right? Sum of local observables. Now, it's pretty trivial that in this case, the Fisher information, since these spins are all uncorrelated, the Fisher information will scale like n, right? Because you will get, it's going to be the sum of all fluctuations for each independent spin. So f of q is going to be proportional to f times some Fisher information density f of q, but that is going to be a number finite. Okay? And in this case, delta theta is going to be greater and equal than 1 over 4n times n times eta. Let us consider now a different situation, a rather opposite situation. Imagine that your state is not a product state like this one, but is a maximally entangled state, in which all spins are, I think it's called a GHZ state, but I don't remember who is G, who is H, and who is Z. And imagine that, again, you do something similar. You pick your observable. In this case, since we chose a definite direction, let's pick as our favorite observable sum over 1 to the n of sigma zi. Okay, so now, as a matter of fact, you see immediately that the average with respect to O of psi of, the average with respect to psi of O is equal to 0, right? And at the same time, you see that this is equal to n squared. Because you have infinite range correlations. And therefore, what you obtain is that in this case, the Fisher information f of q goes like n squared times some number, and your Kramer-Rabault is going to be much better. So it's going to be this number times n squared times n.
Sorry, could you explain again why O squared gives n squared? Because it looks like square of each sigma z is 1, and the cross product of two sigma z's should be an average 0, right? So it should be n, no? Or I'm wrong?
Just a second. No, it is n squared for the simple reason that here it was 0 because of symmetry, because
Yes.
you had 1 sigma z. But here you have 2, right?
Yeah, so
You get from terms like up, sigma xi, so imagine, writing this, you will have up here on the right, sigma zi, sigma zj, up. And that will be n squared terms, plus down, sigma zi, sigma zj, down. But since these are two operators, you will not flip the sign. You see what I mean? No. Should I go?
Okay.
So it is like this, up, up,
Okay, good.
sum over ij, sigma
Good,
zi,
yeah.
sigma zj, up, up, plus, down, sigma zi, sigma zj, down. Now you see that when I had 1, here I was getting a minus sign. But since here I have 2, I get a plus sign also here. These two sum up. Okay?
Yeah, that's good. I just mislaid the sigma z and sigma x. I thought that it should,
Oh, if it is
it
sigma
should
x,
flip,
is that,
and,
okay.
and this is
Sigma
just
x is a
multiply on.
different story.
Okay,
Okay.
good.
Right?
That's clear. Thanks.
Okay, so this limit in which the best accuracy is bound by 1 over n squared, which is a much lower, it's a lower bound than that one, is called the Heisenberg limit. Well, this one is called shot noise limit. So this is practically the reason why, you probably heard this, in so-called quantum metrology, you can use entanglement to improve the accuracy of measurements. Exactly because of this, because you can, when you measure, when you have a state that is uncorrelated like this one, your rotation is applied to each individual spin by itself, right? There is no correlation whatsoever. So it's like doing n measurements of the spins. Every time you perform the experiment is like looking at each spin independently. That's why it's called shot noise, because it's the noise you get when you have current, incoherent electrons passing through a point contact, for example. In this case, they're not incoherent at all. They are all correlated with each other. And that is why you get an improved accuracy. But what is interesting in these expressions is that, you see, if I think of taking the Fisher information and I divide it by n, in this case I will get a number, so f of q. Well, in this case, I will get something proportional to n. And this is something that is actually a bit more deep than these two examples. There is a sort of, I can call it a theorem if you want. You can read it in Petze's Maths in the proof. It tells that if I have, if my Fisher information density is greater than or equal than k, then, no, let's do it in a different way. Imagine picking a state, and imagine considering the set of, for a spin system, the set of all possible local operators of this form, where sigma are polymatrices and n's are unit versors. Then define the quantity f of q equal to the maximum over all the possible versors of f of O of n if f of q divided by n is greater than k, then it means that your state is k plus 1 entangled, which means that the state can be written in a form in which there are at least a k plus 1 parties, k plus 1 degrees of freedom that are irreducibly entangled. So you see, in this case, for example, the Fisher information is greater than n, is equal to n. So which tells us that this state has n parties that are irreducibly entangled. You cannot disentangle them. You cannot take one of these guys and take it out of this and write it as a product state of one of these guys and the rest. No, they're all sitting there. Okay? So what I wanted to say is that this quantity does not only give you information about precision with which you can infer measurements, but it gives you also information about how many parties in your state are entangled. That's the statement. All right, so now that I gave you a long introduction about the Fisher information, let's go back to Kitaev. So we are interested in figuring out whether this quantity could give us information about whether our system is in a mixed state or in some pure state that looks mixed from the point, looks thermal from the point of view of all possible local measurements. This is the question. So let's first imagine that it was in a mixed state. In a thermal state like this. This is a perfectly legitimate thermal state for some given Hamiltonian. Right. In this case, and I leave it to you as an exercise, because it's really, people wrote a PRL about this not many years ago, but it's really a very simple exercise to prove this for some reason. I leave it to you to prove that the Fisher information associated to an operator O for this density matrix is going to be equal to 2 over pi integral d omega tangent hyperbolic of beta omega over 2 times the imaginary part of the response function, the Fourier transform of the response function of the operator O. The one we wrote this morning, okay? So let me remind you, for those who were not here, this response function is minus I theta prime. Okay? How do you prove this? Well, you remember the formulas that I wrote down before, the one by Braunstein and Capes. So you have to prove that that with these coefficients is equal to this. What you have to do is the standard thing that you read in any book of many-body physics, chapter 1 or chapter 2. You write down the Lemon representation for your correlation function, for the Fourier transform of your correlation function. There's going to be a bunch of delta functions there. You do all the integrals, and you will get that this is exactly equal to the Braunstein-Cave result. So that's why I'm saying it's quite impressive that this result had to expect, had to wait until 2000 and I don't know, 20 in order to be discovered.
So
Yes?
how to understand this formula that on the left hand side we have like quantity with one physical meaning, and on the right hand side there is transformation of quantities which have also different meanings and they are equal to the first quantity. How is it working?
I define what is meaning.
But then, okay, if we look just at Fisher entropy, I
Yeah,
thought
so
it's like
this is a
distribution.
mathematical statement, right? So this is equal to sum over I and j, pi minus pj squared, pi plus pj, all I and j, nothing matters squared. So
So
this
from
is
a operator with the measurements, we obtain some statistics.
no, not do measurements. This is it. So this is the definition.
Yeah, but P is the probability to get from measurement.
Yeah, but in this case, you know what is P. P is not a probability of measurement. P are the coefficients of the diagonal representation of the density matrix. They're not results of measurements. I think you're confusing the two P's. I apologize. There are not enough letters in the alphabet. So sometimes I have the same information for the same letter. Two different types of information for the same letter. It's complicated. So this P is not the Fisher probability distribution. This P is the this is sum over I, pi, I. Okay? So these P's are the coefficients of the diagonal representation of the density matrix. And I mean, this is an equilibrium state. It's weird. I mean, when I look at this, it seems to me the most natural thing, right, to do, because this is a squared. So, and when you compute correlation functions, typically you get products of matrix elements. And we have seen it before when we have done the fluctuation dissipation theorem. And well, the idea here, I don't know, I mean, they just they just had to find this in order to make these two consistent with the lemon representation of this correlation function, and it works. So what is the meaning? I don't know. It is like this.
Isn't this expression similar to the sum rule for example, to the sum rule?
Yeah, I mean,
Do you remember who wrote this paper? So
Marcus Heil, Zoller, and others. Tagliacozzo, Zoller, Heil. Tagliacozzo. Zoller, Heil. Okay. So, right. So this is one thing. The other thing is, okay, so this is for the mixed state. What about pure state? Well, first of all, we can rewrite this in a nicer form. Since this is it's equilibrium, so it satisfies the fluctuation dissipation theorem. Here we will have that S of omega is equal to 2 cotangent hyperbolic of beta omega over 2 pi the root prime of omega. And therefore we can rewrite this as 2 over pi, or 4 over pi, no, 1 over pi, integral d omega of tangent hyperbolic beta omega over 2 times S of omega. Tangent hyperbolic squared. Okay? I just use the fluctuation dissipation theorem, plug it in here, and that's what I get. Now, what about a pure state? Well, for a pure state, so imagine that now we have a pure state, a pure thermal state. Pure state, not a mixed state. A pure state that looks thermal from all local measurements, etc., etc. So the Fisher information for a pure state is this, where this is our thermal state. But wait a second, this I can write it as 2 expectation value of the, so there is a factor of 4 here, 2 the expectation value of delta O of T.
So this is pure state or thermal state?
Sorry?
This is thermal state now or pure state?
No, it's a pure state, but psi-thermal means that it's is an excited state for which the ETH is valid. Right? At T equal to T prime, but this is a symmetrized correlator at equal times, so I can write it as 1 over pi integral d omega of S of omega. So an equal time correlation function, I can always write it as the integral over all omegas of its Fourier transform. Notice that this S of omega is the same S of omega that is sitting here because I'm in thermal equilibrium. So they will have the same inverse temperature, is the same S of omega. So what I see, if I compare, since the tangent hyperbolic is always smaller than 1, tangent hyperbolic square is positive, but this is always smaller than 1. I see that, let's call this, I don't know how to call it, pure. And that is, we call it impure. So F pure O is always greater or equal than F mixed. Okay? So, if I have a state that is thermal, and if I have an eigenstate of my Hamiltonian that satisfies ETH, blah, 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 etc., is in the center of the spectrum, and so on and so forth, I will always have that the pure state has a Fisher information that is greater or equal than the mixed state with the same inverse temperature. Okay? Now, one could say, okay, so my advisor when I was doing my PhD was always telling me, who cares if something is greater than something else? It's important only when there is a qualitative effect. And qualitative effect could be if this one, for example, is divergent with system size and this one is finite. This is a qualitative effect. Well, it turns out that this is what happens, for example, when you have a system that has at finite temperature a phase diagram of this type. So it has, with respect to some parameter of the Hamiltonian, it has a quantum phase transition and then some thermal phase transition sitting above it. For example, for Ising model, quantum Ising models in 2 dimensions. This could be the case for certain systems with long-range interactions in 1 dimension, and so on and so forth. Now, when you have a phase diagram of this type, so you see it here as a function of temperature, but temperature can be always traded with energy density when you think microcanonically. So this phase transition, you could think it as occurring as you increase the energy density in your spectrum, right? So imagine that I go to states that are more and more excited with an energy density that is increasing and increasing and increasing. Eventually, I will be moving from the ground state that is sitting here in this direction and cut through this point. Now, it's quite interesting that if you go to the paper by Tagliacozzo and company that I mentioned before, they did a similar calculation for this nice definition, nice expression in terms of the response function they found for the Fisher information for the mixed state. And there was no signal whatsoever of the phase transition occurring. Fisher information stays always finite, is a number. If instead you do the calculation of what happens for a pure state as you increase the energy density, so you go to more and more excited states, you will get that the Fisher information for the pure state, let's say you calculate it for O, that is the order parameter of your transition. You know that the order parameter has divergent fluctuations at the critical point. And you will get that this goes like n to the power gamma mu minus 1. Right. So there is a qualitative effect, for example, close to thermal phase transitions. So all of this to say that it makes perfect sense to think of this quantity of, okay, well, let's be honest, it's not easy to measure or to think of measuring the quantum Fisher information. It's a bound, it's something that bounds, it's a length or whatever in the parameter space, but it's essentially a bound for metrological experiments, for accuracy of metrology. But in a rough sense, it's telling us that this quantity is possibly able to distinguish between a mixed state and a pure state in a qualitative way. Okay? Now, let's come to now the final part, which is what about, where is it? What about other possibilities? So now I have 15 minutes, so let me briefly mention the answer that Kitaev gave to his own question, which is the OTOC. I honestly, okay, he introduced this concept in a talk that he gave, and you can find on YouTube. It's 15 minutes, so you can watch it multiple times. And this is what I did in order to understand what he was talking about. I watched it many times, and it's still obscure to me how he was reasoning. I mean, to my understanding. But it's very interesting. So the question is, I already mentioned, it's a very deep question. And the answer he gave is, let's try to compute instead of computing since all response functions will essentially be constrained by the fluctuation dissipation theorem in the case of, for a system that thermalizes, from calculation of 2-point functions or 1-point function, you will never be able to distinguish between a pure state that looks thermal and a thermal state that is mixed. So the idea is roughly, let's consider higher order correlation functions. But for some reason, in order to avoid possibly rewriting these higher order correlation functions as product of two-point correlation functions, he decided to consider correlation functions, C of t, that are essentially have a strange time ordering. So for example, B of t, A of 0, commutator squared, something of this sort. So this is an example of what people would call an RTOC, out of time order correlation. Out of time order because you have an operator at time 0, then an operator at time t, then another operator at time 0, and then another operator at time t. So it's, well, we will be discussing it next time, but this is not something that you can easily represent on a Keldysh contour. Let's put it this way. Now, what is this object? Why it is, so first of all, let me mention why it is something that might give you information about the fact that you're not in a thermal state. The reason is that if you go through the calculation of these objects and you employ the eigenstate thermalization hypothesis, in that case you will have to use same operators here, you will see that in order to do the calculation, at some point you will have to assume something about possible correlations, of different matrix elements of the statistical factor. And this is something we didn't do. We didn't impose anything on this. So we don't need to think about this in order to prove fluctuation dissipation theorem with ETH. And the point is that as you start computing higher order correlators like this one, you start seeing the structure of R and M as a matrix, not just from the point of view of single matrix elements. And you start getting information about it. And that is something interesting and useful. Now, from a practical point of view, then you can ask me, what is this? So let me tell you how I understand it. Where is it? Just a second. Here it is. So let me tell you how I understand it. Imagine that you have a certain operator A that is concentrated on a certain point in your physical space, for example, sigma z I, and a certain operator B that is living somewhere else. And you want to study how correlations between these two operators develop as a function of time as you crank up your dynamics. Now, of course, initially B and A will commute. But as you turn on the dynamics, in principle, B of t, which is e to the IHT, e to the minus IHT, at some point will start not commuting with A, which is something that you can detect, for example, by Lieb-Robinson bounds on the correlations. Now, of course, I mean, the fact that these two start not commuting means that at some point you have a response on the fact that you're introducing, it's in practical sense, means that if you're introducing in your Hamiltonian a perturbation proportional to A or to B, At some point, this perturbation is going to be to have an influence on B, right? That's the point. And you can see this by studying the correlation function, the response function. Like this one. But, as we already said, such response functions will have absolutely no information on whether your system is pure, mixed, whatever. If it is thermalizing, you will see just thermal physics and nothing else. So can we now generalize this idea to something more complicated, to higher order correlations? Well, one thing we can think of doing is, if in a situation in which this guy has an influence on this operator, so at some point correlations reach A, you can think of applying a rotation generated by B of T on A, and this rotation is going to be non-trivial. So it's going to generate an operator A delta of theta that is non-trivial. And this A delta of theta is of course equal to A plus I delta dTA plus I all others. Now, imagine that now we consider how much this rotated operator differs from the original one. If we average this over our state. Now, if we take the average, we will get that this is minus I delta dTA. So we will get the response function, essentially, up to the theta. If we consider the fluctuations, so we consider A theta delta T minus A squared, then this is equal to minus delta squared dt A squared average. So it's minus delta squared times what I call the out of time order correlator. So essentially this is physically what is the out of time order correlator, nothing else, right? So it's just quantifying the difference between the operator and the rotated operator once you let your system time evolve. You can do a lot of other interesting manipulations, but I don't want to. I just wanted to tell you what it is physically. Now, why it is interesting? Well, it is interesting because it's much more complicated than the feature information to understand the physical meaning of this object. There is only one particular case where it is simple, and that is a system that has a good semi-classical representation. For example, infinite range models. In infinite range models, it turns out that this quantity, for example, if you have a infinite Kitaev model or infinite ranges in model, etc., it turns out after a short time transient in which it grows quadratically in time to start growing exponentially. And the exponent with which it grows, which is the analog of a Lyapunov exponent, has the property that is always smaller or equal than 2 pi over beta, where beta is the inverse temperature of your system. This is why high energy people got excited about this, because they're interested in black holes, perfect scrambling, etc., etc., etc. Now, after this transient, which is exponential only for these specific systems. Because if you don't have a system with infinite range interactions or with a good semi-classical system, but you have a system with, you know, short range interactions and a local Hilbert space that is finite, you will never see an exponential, you will see a nice power law. Eventually, the OTOC saturates to some value. And the last part of the dynamics is something that you can actually obtain from ETH by assuming ETH. Assuming ETH in the sense that you assume that your matrix Rnm is not only, I mean, you don't know just the statistics of this matrix element, but you assume that it's a Gaussian random matrix. If you assume that it's a Gaussian random matrix, you can use ETH to do all sorts of calculations, and you will get that higher order correlations can be written as products of two-point correlation functions, as in standard diagramatics, by the way. You can use the Ann-Lokovic theorem, so on and so far. Now, but unfortunately, all of this, you can use it only for asymptotic dynamics. For the transient, everything is dominated by a structure that is dictated by the initial state and has information about something that is beyond the eigenstate determinalization hypothesis. How beyond? Well, there are some studies now. Silvia Pappalardi is doing some work. All of this is at the frontier, and I think it's too much to tell in this class. So it's a very interesting subject. If you're interested in it, you can read so you digit in your web Galilei, and Pappalardi. And you will find some lecture notes by Silvia Pappalardi, who was my student, who has done some very interesting work on extensions of ETH to describe the physics of OTOC, using free probability, free cumulants, and complicated mathematical stuff. You will find it in the lecture notes that you will get on the web to this. So I will not go into details at the moment. I want to. Yes?
So just to conclude, like the question was how to check and maybe experimentally how system which is in mixed state differs from system in pure state, something like this. So can you repeat the question and the answer?
Well, so the answer is, if you look at a quantity like this, the long time dynamic, so you can take this object, you can do the calculation of this object assuming ETH with Rnm that is a random matrix, Gaussian random matrix. You will get that the C of t can be written as products of two-point correlation functions, but then you compare this with numerics, for example, or with other more complicated analytical calculations, and you discover that all the transient physics cannot be described by ETH, right? So all the physics from time t equal to 0, from all the way to, well, it depends, because when ETH kicks in depends on the bandwidth and on various details, has to be described by, is described by other stuff, right? So you will see that, okay, the bottom line is, you will see the difference between the pure state and mixed state in the transient of this quantity, in the time dependence of this quantity, okay? So this is the synthetic statement.
And you understand dependence, mixed, they should be also mixed during whole time, it shouldn't.
So if it is mixed during all times, so if it is just a mixed state and etc., you will see one thing. If it is a pure state satisfying ETH,
I just thought
in a, or if it is a pure state that satisfies ETH but has a structure beyond ETH that you don't see from two-point correlations, you will see at intermediate times. That's the statement.
If we do evolution, then mixed state can stop being mixed and pure state can become mixed, or it will be not the case.
What do you mean a pure state can become mixed?
Some entanglement will appear.
With what? With some external environment?
Somehow, I don't know that it can't not happen. So if we say like we need to do evolution, but I have a question immediately, why this property will be constant, protected through the evolution? Maybe it will just change, that's all.
I don't understand the question.
So, like the question is how to determine different states. You say we do evolution and we see how out of time ordered correlation functions change during this evolution, right? Something different that you were saying.
No, what I'm trying to say is that if you assume that your state is thermal, satisfying ETH, with uncorrelated RNN, or you have a structure that is beyond ETH due to correlations that are not detected by two-point functions, you will see this in the intermediate time dynamics of this square correlator. While, and this is the statement, you will not see anything in the, if you don't take the square. This is interesting, right? 4-point correlation functions of this complicated sort will see in intermediate time structure that is beyond ETH, while 2-point correlations will not see anything. So this is my statement. Okay, so next Friday we will start with Keldysh then.
Thank you.